For most of the human story, there was never just one kind of human. Neanderthals lived across Europe. Denisovans moved through Asia. Earlier human species survived in distant parts of the world, while our own ancestors were still spreading beyond Africa. Only very recently did Homo sapiens become the last human species left. To understand how that happened, this documentary travels back roughly 7 million years to the first primates that started walking upright on the plains and forests of Africa. It moves through the rise and disappearance of several different human species, and it ends as scattered farming villages gradually become the first cities, at the threshold of written history. Along the way, there will be stone tools, fire, ice ages, and long ocean crossings. There will be the slow, uneven emergence of language and art. There is no need to track every date or every name. You can drift in and out as you like, and the story will keep moving forward regardless. We begin in a warm, wooded stretch of Africa, several million years before anything resembling a modern human existed. Around 7 million years ago, the ancestors of humans and the ancestors of chimpanzees were still one population. They lived somewhere in Central Africa in a landscape of mixed forest and open woodland. Genetic comparisons between living humans and living chimpanzees let researchers estimate roughly when this shared population split into two lineages. The exact date remains difficult to pin down. It continues to shift slightly as new genetic and fossil evidence accumulates. What matters more than the precise year is the pattern that followed. One branch of that ancestral population continued much as before, eventually giving rise to modern chimpanzees and bonobos. The other branch began changing in a specific direction. It gradually favored a posture no other ape had settled into so completely, walking upright on two legs as the primary way of getting around. The fossil evidence for this earliest period is thin. It has been pieced together from a small number of sites and a limited number of bones. Any description of this stage of human history involves real uncertainty. Even so, a few individual fossils have shaped much of the current picture. A skull discovered in Chad, dated to somewhere around 7 million years ago, was given the name Sahelanthropus. It shows some features that hint at upright walking, based on the angle at which the skull would have balanced on the spine. This interpretation is not universally accepted among researchers, since the skull itself is heavily distorted, and no clear pelvis or leg bones were found alongside it. A few million years later, a partial skeleton from Kenya offers firmer evidence. Roughly 6 million years old, and known as Orrorin, it includes a thigh bone with features more directly suggestive of upright walking. The clearest and most complete evidence from this period comes from a slightly later fossil. Discovered in Ethiopia, it is known by the name Ardipithecus ramidus and dated to around 4.5 million years ago. Unlike the earlier finds, this skeleton is unusually complete. The parts of the body used to study locomotion, the pelvis, the feet, and the leg bones, all point to an animal capable of walking upright on the ground. At the same time, it retained a grasping big toe, well suited to climbing through trees. This combination points toward a gradual transition rather than a sudden switch from tree-dwelling to ground-dwelling life. It was testing a new way of moving across open ground without yet fully abandoning the forest canopy that had sheltered its ancestors for millions of years. why walking upright became useful enough for natural selection to favor it remains a debated question. Several explanations have been proposed rather than a single settled answer. One long-standing idea points to Africa's changing climate during this period. As certain regions grew drier, forests gradually gave way to patchier woodland and open grassland. This made it useful for an animal to travel further between scattered food sources without spending as much energy. Other researchers have proposed that upright walking freed the hands to carry food, infants, or tools, offering an advantage independent of any particular habitat. Still others have pointed to simple thermoregulation. Standing upright exposes less of the body's surface to direct overhead sun during the hottest part of the day, potentially reducing the risk of overheating on open ground. These explanations are not mutually exclusive. The true picture likely involved several overlapping pressures, working together across a long stretch of time, rather than any single decisive cause. Whatever combination of pressures drove it, walking upright turned out to be an unusually consequential change. It reshaped nearly every part of the body built around it. The pelvis grew shorter and wider to support the trunk in an upright position. The spine developed a distinctive curve to keep the head balanced directly above the hips. The big toe gradually lost its ability to grasp branches like a thumb. It aligned instead with the other toes, forming a stable platform for pushing off the ground with each stride. None of these changes happened quickly or all at once. They unfolded across millions of years, through countless small shifts in bone shape and muscle arrangement, each one slightly improving the efficiency of a two-legged stride. By around 4 million years ago, a new group of hominins had appeared across eastern and southern Africa. They were more fully committed to upright walking than their predecessors, and recognizable enough to be placed in their own genus, Australopithecus. The most famous representative of this group is a partial skeleton discovered in Ethiopia in 1974, nicknamed Lucy. It belongs to the species Australopithecus afarensis, dated to around 3.25 million years ago. Lucy stood roughly a meter tall. Her brain was not much larger than that of a modern chimpanzee. Her skeleton combined clear adaptations for upright walking with arms still proportionally long and curved fingers well suited to climbing. She would have moved comfortably across open ground on two legs. She would have remained capable of climbing into trees for food, safety, or sleep, much like the rest of her species. Direct physical evidence for this upright gait comes from an exceptional site in Laetoli, in what is now Tanzania. A layer of volcanic ash dated to around 3.5 million years ago preserved a trail of footprints. At least 2 individuals had walked side by side across the still damp surface. The stride pattern, the placement of the heel and toe, and the overall shape of the footprints closely match what would be expected from a fully upright walker. This offers direct physical confirmation of a capability that fossil bones alone can only imply. The ash hardened not long after the tracks were made. It preserved a single ordinary walk across a single ordinary afternoon, frozen for over 3 million years until its rediscovery in the late 20th century. Australopithecus was not the only hominin lineage moving through Africa during this period. Around 2.5 million years ago, a separate and more heavily built group appeared, generally placed in a genus called Paranthropus. These robust Australopithecines, as they are sometimes called, developed massive jaws, large flat molars, and a pronounced bony ridge running along the top of the skull, called a sagittal crest, which anchored powerful chewing muscles. This anatomy points to a diet built around tough, fibrous plant food requiring extensive grinding, a specialization quite different from the more varied, flexible diet favored by their slighter Australopithecus relatives. Paranthropus persisted for well over 1 million years, surviving alongside early members of the genus Homo for a considerable stretch of time before eventually disappearing. From the fossil record around 1 million years ago, its extinction remains only loosely understood, though some researchers suspect that its narrow dietary specialization, an advantage during periods when tough plant food was abundant, may have become a liability as African climates grew more unpredictable, favoring instead the broader, more adaptable diet and behavior of the Homo lineage. This pattern, a highly specialized species eventually losing ground to a more flexible, generalist relative, appears more than once across this long history. The world. Lucy and her relatives inhabited was not the dry, empty savanna sometimes pictured in older accounts. Fossil pollen, ancient soils, and the remains of other animals found alongside. Australopithecine bones point to a mixed landscape, patches of woodland interspersed with more open grassland, threaded by rivers and seasonal lakes. This kind of mosaic environment likely rewarded exactly the flexible lifestyle these early hominins seem to have led, comfortable moving between trees and open ground, adjusting their diet to whatever was available as the seasons shifted. Picture a small group moving across this landscape in the early morning, before the day's heat had fully settled in. Ahead lies a stretch of open grassland, dotted with acacia trees, and crossed by the tracks of antelope and other grazing animals that shared this world. Behind them, a denser stand of trees offers shade, fallback food in the form of fruit and leaves. A place to retreat if a larger predator, one of several saber-toothed cats or giant hyenas that hunted this same landscape, happened to appear nearby. This was a world shared uneasily with animals significantly more dangerous than any hominin present. And safety, for a small, slow, still only moderately intelligent primate, depended heavily on staying close to trees, staying alert, and staying together as a group. That diet, based on the wear patterns and chemical signatures preserved in fossil teeth, appears to have been broad and largely plant-based. Studies of tooth enamel from several Australopithecine species point to a diet built around fruits, leaves, and underground plant parts such as roots and tubers. This was supplemented at times by foods with a chemical signature suggesting the presence of grasses or sedges, a detail that surprised researchers when it first emerged, since apes today rarely rely on this kind of food source. Some researchers have suggested this reflects a broader dietary flexibility, allowing certain hominin lineages to survive in a wider range of habitats than a narrower, more specialized diet would have permitted. Australopithecus was not a single, unchanging species holding steady across this entire period. Several related species appeared across different regions and different stretches of time, sharing the basic body plan first tested by Ardipithecus and its relatives, while diverging in smaller details of skull shape, tooth size, and body proportion. In southern Africa, a related form known as Australopithecus africanus left behind fossils including the town child a partial skull of a young individual discovered in 1924. It became one of the first pieces of strong evidence that human origins lay in Africa rather than in Europe or Asia, a conclusion many researchers at the time were reluctant to accept. By around 2.5 million years ago, one branch of this broader hominin family began showing changes that mark a meaningful shift in this long story, a modest but real increase in brain size, alongside the first clear evidence of deliberately shaped stone tools. This marks the point where researchers generally begin using the term Homo, the same genus that includes our own species. The boundary between late Australopithecus and early Homo remains blurry in the fossil record, with several transitional fossils that resist being placed cleanly on one side or the other. A discovery reported in 2015 has complicated this picture in an interesting way. At a site called Lumekwi 3 in Kenya, researchers uncovered stone tools dated to around 3.3 million years ago, some 700,000 years before the earliest confirmed Homo fossils. No hominin remains were found directly alongside these tools, so their maker cannot be identified with certainty. Though Kenyanthropus, a contested and poorly understood hominin genus known from the same region and period, remains one candidate, alongside the possibility that an as yet unidentified Australopithecus population produced them instead. Whatever the answer, this discovery suggests that the capacity for deliberate tool-making may have appeared earlier and in a wider range of hominins than researchers assumed for most of the 20th century. The earliest confirmed stone tools associated specifically with the Oldowan tradition, discovered at sites in what is now Kenya and Ethiopia, date to around 2.5 million years ago. These tools were simple by later standards, produced by striking one stone against another to knock off sharp flakes. They represent a new kind of sustained, repeated behavior, the deliberate shaping of a natural object into something better suited for cutting, scraping, or pounding. Wear patterns on some of these early tools, along with cut marks found on animal bones from the same sites, suggest they were used for processing meat and marrow, extracting a source of concentrated nutrition that would have been difficult to access without a sharp cutting edge. It remains uncertain exactly which hominin species produced these earliest tools, since several different types of hominin lived in the same regions during this period, including late Australopithecus populations and the earliest members of Homo. Some researchers have proposed that stone tool use may have begun before the emergence of Homo as a distinct genus, meaning the capability may have developed within a population still closer to Australopithecus in overall anatomy, though this remains a topic of active investigation rather than settled fact. The species most closely associated with this early tool-making tradition is Homo habilis, whose name means handy man, reflecting the assumption researchers made when the species was first described in the early 1960s. Homo habilis had a brain noticeably larger than that of Australopithecus, though still significantly smaller than that of modern humans, along with a skull shape and tooth structure that mark a real, if modest, step toward the later members of the genus Homo. Whether Homo habilis represents a single coherent species or a loose grouping of several closely related but distinct forms remains debated among researchers who study this period closely, since the available fossils show a fair amount of variation in size and shape. Some of that variation has led certain researchers to recognize a second, contemporary species. Homo rudolfensis, known from a partial skull discovered near Lake Turkana, with a noticeably larger brain and different facial proportions compared to typical Homo habilis specimens. Whether this represents a separate species, simply a larger individual within a naturally variable Homo habilis population, or even a male and female of the same species showing ordinary size differences between the sexes, remains unresolved. Illustrates a recurring difficulty in this field, working out how many distinct species existed at any one point in human prehistory, when the surviving fossil evidence for any given period usually consists of no more than a handful of partial skulls and scattered bones, from which researchers must reconstruct an entire population's range of natural variation. By around 1.9 million years ago, a more decisive change appears in the fossil record, marking the arrival of Homo erectus, a species that would go on to become one of the longest-lived and most widely distributed hominins in the entire human story. Compared to earlier members of Homo, Homo erectus had a noticeably larger brain, a body with proportions much closer to those of modern humans, including longer legs relative to arm length, and a skull with a lower, flatter profile and a pronounced ridge of bone above the eyes. An unusually complete skeleton discovered in Kenya near Lake Turkana, and known informally as Turkana Boy, offers a detailed picture of this species rarely available from a single find. Belonging to a boy who died around 1.5 million years ago, the skeleton shows a body built for efficient long-distance walking and running. Researchers estimate he was roughly 8 to 9 years of age, based on his skeletal development. His narrower pelvis and rib cage, compared to earlier hominins, are more similar in overall shape to that of a modern human than to Lucy and her relatives. This body plan connects to a broader shift in how Homo erectus likely lived. Longer legs and a more efficient stride suggest an animal capable of covering long distances economically, a useful trait for an active hunter or a persistent scavenger following herds of grazing animals across open country. Some researchers have proposed that Homo erectus practiced a form of hunting, sometimes called persistent hunting, chasing prey animals over long distances in the heat of the day until the animal, unable to cool itself as efficiently as a sweating, upright human, became exhausted enough to approach safely. This idea remains difficult to confirm directly from fossil evidence, though the body proportions of Homo erectus are broadly consistent with the demands of sustained, long-distance movement. Throughout this part of the story, and for millions of years afterward, Earth's climate was cycling through a long, repeating pattern of glacial and interglacial periods, driven largely by small, regular shifts in the planet's orbit and the tilt of its axis. Changes first worked out in detail by the astronomer Milutin Milankovitch in the early 20th century. Roughly every 100,000 years, give or take, the planet swung between colder glacial periods when ice sheets expanded across much of the northern hemisphere and global sea levels dropped, and warmer interglacial periods similar to the climate of today. Every hominin population across this long history lived through numerous cycles of this kind, and these repeating swings in climate, sea level, and habitat likely played a constant background role in shaping where populations could live, which routes lay open for migration, and which species ultimately thrived or struggled during any given stretch of time. Homo erectus also achieved something no earlier hominin is known to have managed, leaving Africa entirely. Fossils and stone tools attributed to this species or to very closely related forms, have been found as far afield as Georgia in the Caucasus region, dated to around 1.8 million years ago. Similar finds appear at sites across South and East Asia, including the well-known locations at Zhoukoudian in China and on the island of Java in Indonesia. This spread across 3 continents happened well before the emergence of Homo sapiens, showing that the capacity for wide geographic dispersal was not unique to our own species, but had already appeared in a more limited form deep in the human lineage's history. Consider what a single generation of that outward movement might actually have looked like. A family group, following a river valley east, finds the familiar plants of home growing thinner each, replaced gradually by unfamiliar trees and unfamiliar animal tracks. There is no plan to cross a continent. There is only the next valley, the next herd of grazing animals, the next stretch of water worth following. Children born partway through the journey grow up in a landscape their grandparents never saw. And by the time descendants reach the far side of Asia, tens of thousands of years and countless such small, unremarkable movements later, no single person along the way would have known they were taking part in anything resembling a migration at all. The Georgian site, known as Deimanisi, has produced an unusually rich collection of skulls, 5 in total, from a single population living in the same general place and time. Rather than confirming a single, uniform picture of early Homo erectus anatomy, these skulls show a surprising degree of variation in size and shape. This variation is wide enough that, had the specimens been found scattered across different sites and different time periods, some researchers might well have classified them as entirely separate species. Found together at a single site, however, they instead offer a valuable caution about how much individual variation a single ancient population could contain. A detail worth bearing in mind whenever fragmentary fossils from different times and places are used to define the boundaries between one hominin species and another. One skull from this same site belonged to an elderly individual who had lost all but one tooth well before death. It shows extensive bone remodeling around the empty tooth sockets, indicating this person survived for a considerable stretch of time after losing the ability to chew food effectively. This suggests that some level of social support for the old or infirm may have existed within this population as well, well over 1 million years before the similar evidence found at Shanidar Cave. Exactly how Homo erectus managed to survive and spread across such a broad range of climates and environments remains an area of ongoing study. Several threads of evidence point toward a more capable, more flexible way of life than any earlier hominin had achieved. Stone tools associated with Homo erectus show real skill in their construction. A more standardized and symmetrical form, known as the Acheulean hand axe, first appeared in Africa around 1.7 million years ago. It reflects a level of planning beyond the simpler old Awan tools of earlier periods, suggesting a hominin capable of holding a mental template of a finished tool in mind before beginning to sculpt the stone. What stands out most about the Acheulean hand axe is its sheer stability as a design. Once this basic teardrop shape appeared, populations across Africa, Europe, and parts of Asia continued producing broadly similar tools for well over 1 million years, with only gradual, modest refinements in symmetry and craftsmanship along the way. a technology remaining in continuous use for a span of time longer than the entire subsequent history of Homo sapiens, suggests either remarkable cultural conservatism, a design so effective that little pressure existed to change it, or some combination of both. A pace of change, almost impossible to imagine, set against the rapid technological shifts of more recent human history. A significant, though still debated, development associated with this period is the controlled use of fire. Some sites in Africa show possible evidence of fire use associated with Homo erectus, dating back well over 1 million years. Clear, unambiguous evidence of controlled, repeated fire use, as opposed to the aftermath of a natural wildfire, becomes significantly more common and more widely accepted from around 400,000 years ago onward. Fire offered several advantages once it came under reliable control: warmth in colder climates, protection from predators, extended hours of activity after dark, and, perhaps most significantly, the ability to cook food. Cooking changes food in ways that matter enormously for an animal trying to extract as much energy as possible from a limited diet. Heat breaks down tough plant fibers and denatures proteins in meat, making both significantly easier to chew and digest, which in turn means the body can extract more usable energy from the same amount of food and spend less energy on the digestive process itself. Some researchers have proposed that this shift toward cooked food may have supported the increasing brain size seen across the Homo lineage. The brain is an energetically expensive organ, consuming a disproportionate share of the body's total energy budget, even at rest. Any dietary change that freed up additional energy could plausibly have supported its continued growth. This idea, sometimes called the cooking hypothesis, remains debated. The timing of widespread fire use and the timing of major increases in brain size do not align perfectly across every reconstruction of the evidence. Even so, it remains one of the more widely discussed explanations for a puzzling trend in human evolution. A larger brain came with a cost that extended well beyond simple energy consumption, one closely tied to upright walking itself. The narrower pelvis required for efficient two-legged walking placed a hard physical limit on how large an infant's head could grow before birth without risking serious complications for both mother and child. The solution that emerged across the Homo lineage involved giving birth to infants at an earlier, less developed stage than most other primates, with a large share of brain growth continuing after birth rather than before it. This left human infants unusually helpless for an unusually long stretch of time compared to other animals, unable to walk, feed themselves, or survive independently for months or years after birth. A genuine burden on mothers and, likely, on wider family and social groups who would have needed to help share the load of caring for such a slow-developing child. Some researchers argue this extended period of dependency, whatever its costs, also created space for an unusually long period of learning, social bonding, and brain development to occur outside the womb, potentially helping explain the flexible, socially embedded intelligence that came to distinguish the human lineage from its closest primate relatives. Homo erectus persisted for an extraordinarily long time, with some populations in Southeast Asia potentially surviving until as recently as 100,000 years ago, based on contested dating from a site on Java, making it one of the longest surviving hominin species known. One of the more startling discoveries connected to this broad period of Homo erectus dispersal came in 2003. on the Indonesian island of Flores. Researchers there uncovered the remains of a small-bodied hominin, standing barely over a meter tall, with a brain roughly a third the size of a modern human's, despite living as recently as 50,000 years ago, well within the period when Homo sapiens was already active elsewhere in the region. Named Homo floresiensis and quickly nicknamed the Hobbit in press coverage at the time, this species remains a subject of real debate among researchers. One explanation holds that Homo floresiensis descended from Homo erectus populations that reached Flores and then shrank dramatically over many generations, a process called island dwarfism, in which limited food resources on a small, isolated island favor smaller body size across many animal lineages, not only humans. A separate explanation proposes that Homo floresiensis descended instead from an even earlier and more primitive hominin lineage, one that left Africa long before Homo erectus and has otherwise left no clear fossil trace, making Flores home to a survivor from a much older branch of the human family tree. Both explanations remain actively discussed, and the debate has not been fully settled by the fossil evidence recovered so far. Whatever its precise origin, Homo floresiensis shows that the human evolutionary story, even this late in its unfolding, still held room for real surprises, isolated populations following unexpected paths largely unknown to researchers until the chance discovery of a single cave. While Homo erectus populations continued in parts of Asia, a separate lineage was developing in Africa and, somewhat later, in Europe and Western Asia, one that would eventually lead to several of the human species most familiar from popular accounts of prehistory. A genetic study published in 2023 has proposed a striking and still debated episode within this general timeframe: a severe population bottleneck affecting the ancestors of later Homo lineages, occurring somewhere around 900,000 years ago. Analyzing patterns of genetic variation across modern human genomes, the researchers behind this study estimated that the entire breeding population of these ancestral hominins may have dropped to as few as around 1,300 individuals, sustained at this critically low level for roughly 100,000 years, before slowly recovering. If accurate, a population this small would have placed the ancestral human lineage in genuine danger of extinction, vulnerable to disease, local disaster, or simple bad luck in a way. A larger, more genetically diverse population would not have been. This finding has attracted considerable scrutiny from other researchers, some of whom question the statistical methods used to reach it. It remains an open question whether this proposed bottleneck reflects a genuine near-extinction event or an artifact of the complex modeling required to reconstruct population history this far back from modern genetic data alone. Around 700,000 years ago, a hominin, often labeled Homo heidelbergensis, begins appearing in the fossil record, first in Africa and soon afterward in Europe. This species shows a larger brain than Homo erectus, closer to the lower end of the modern human range, along with a more robust, heavily built skeleton suited to a physically demanding way of life. Homo heidelbergensis is widely regarded by researchers as a likely common ancestor for at least 3 later human lineages: the Neanderthals of Europe and Western Asia, the Denisovans of Asia, and eventually, Homo sapiens in Africa. The exact branching pattern connecting these groups remains an active area of research, with new fossil and genetic discoveries continuing to refine the picture. A site called Boxgrove in southern England, dated to around 500,000 years ago, preserves detailed evidence of how these populations lived. Butchered animal bones, including the remains of a large extinct species of rhinoceros, show cut marks consistent with organized cooperative hunting rather than opportunistic scavenging of animals that had died from other causes. A horse shoulder blade recovered from the same site bears a circular puncture mark consistent with a thrown, wooden-tipped spear, among the earliest direct physical evidence anywhere for this kind of weapon in use. Wooden spears themselves rarely survive in the archaeological record. Since wood decays far more readily than stone or bone, meaning direct evidence of this technology, such as the injured horse bone at Boxgrove or the preserved wooden spears recovered from waterlogged sediment at other European sites, is unusually valuable precisely because it is so rare. Sites from this broad period also show evidence of forward planning that extends beyond a single hunting trip. Stone tools recovered at some Homo heidelbergensis and early Neanderthal sites are made from raw material that did not occur naturally at the site itself, sometimes originating tens of kilometers away, indicating either direct travel to a known, favored stone source or some form of exchange with neighboring groups occupying that territory. Selecting and transporting good toolmaking stone across such distances requires a hominin capable of remembering the location of a useful resource well outside its immediate surroundings and returning to that same location or sending others there as the need for fresh material arose. A level of spatial memory and forward planning that continues to complicate any simple picture of these populations as living purely in the moment. A striking piece of evidence connected to this period comes from a cave in northern Spain called Sima de los Huesos, meaning pit of bones, where the remains of at least 28 individuals, dated to around 400,000 years ago, were found at the bottom of a deep vertical shaft. The circumstances suggest deliberate placement of the dead by other members of this group. The location shows no evidence of a natural trap and appears to have required deliberate effort to access, raising the possibility of intentional, repeated behavior connected to the dead long before the more elaborate burial practices associated with later human species. In Europe and Western Asia, populations descended from this Heidelbergensis stock gradually developed the distinctive features associated with the Neanderthals, a process that unfolded slowly over hundreds of thousands of years rather than through any single sudden transformation. By around 400,000 years ago, and certainly by 200,000 years ago, Neanderthals had become a recognizably distinct population, adapted to the colder, more variable climate of Ice Age Europe in ways that set them apart from their African relatives. Neanderthal anatomy reflects this cold-adapted lifestyle in several ways. Their bodies tended to be shorter and more heavily built than those of modern humans. A body shape that conserves heat more effectively by reducing the ratio of surface area to body mass. Their brains, on average, were slightly larger than those of modern humans, though brain size alone offers limited insight into cognitive capability, since organization and structure matter as much as raw volume. Neanderthal skulls also show a longer, lower brain case, while Homo sapiens skulls are more rounded and globular, a shape associated with a somewhat different arrangement of certain brain regions linked to memory and social cognition. Translating this kind of anatomical difference into a confident claim about differences in thought or behavior remains difficult, and researchers generally avoid framing it as a straightforward hierarchy of intelligence. given the strong and growing evidence of Neanderthal burial practices, symbolic marking, and deliberate underground construction that points towards sophisticated planning in its own right. Neanderthals occupied a broad and varied range across their long history, stretching from the Atlantic coastline of what is now Portugal and Spain, across most of Europe and eastward into Western and Central Asia, with confirmed sites as far east as the Altai Mountains in Siberia. The same general region where the first Denisovan remains would later be identified. Within this range, Neanderthal populations adjusted their tools and behavior to a wide variety of environments, from the cold steppe of Ice Age Europe to the warmer, more Mediterranean conditions found further south, showing a degree of ecological flexibility that complicates any simple picture of Neanderthals as narrowly specialized for one particular kind of cold, open landscape. Despite this wide geographic range, genetic evidence indicates that overall Neanderthal population size likely remained modest throughout their history, probably numbering in the tens of thousands at any given time across the entire continent, organized into small, scattered, and often isolated groups. Genome sequencing from individual skeletons frequently reveals signs of inbreeding, a pattern typically seen when close relatives interbreed within a small, isolated population over many generations. And this demographic reality may have made Neanderthal populations, for all their evident capability, vulnerable to the kind of sustained pressure that appears to have contributed to their eventual disappearance. For much of the 20th century, Neanderthals were widely portrayed as a crude, unintelligent evolutionary dead end, a portrayal that has shifted significantly as evidence has accumulated. Neanderthals produced a sophisticated stone tool tradition known as Mousterian technology, made fire, and hunted large and often dangerous animals cooperatively. They treated their dead with what appears to be genuine care, including several sites where bodies were placed in shallow pits in what looks like deliberate burial. The extent and meaning of this practice remains debated, since not every claimed Neanderthal burial has held up to closer scrutiny. Much of Neanderthal toolmaking relied on a method called the Levallois technique, in which a stone core is carefully shaped in advance so that a single, well-controlled strike produces a flake of a predetermined size and shape, demanding real forward planning, since the toolmaker had to hold a finished result in mind well before the final strike. Isotope studies of Neanderthal bones, along with wear patterns on their teeth, point to a diet dominated by meat, often from large game such as horses, bison, and reindeer, supplemented at some sites by fish and shellfish. Coastal sites in what is now Portugal and Spain have produced especially clear evidence of this, including mussel and clamshells showing signs of deliberate collection and cooking, and, at one site, the butchered bones of dolphins and seals, pushing back against an older assumption that only Homo sapiens made regular, sophisticated use of marine resources. Wooden spears recovered from a site called Schöningen in Germany, impressively preserved in waterlogged sediment and dated to around 300,000 years ago, show careful shaping and balancing, evidence of hunting technology already in use among the ancestors of later Neanderthal populations. Much of the modern understanding of Neanderthal biology comes from a field that barely existed a generation ago: the direct sequencing of ancient DNA. Recovering usable genetic material from bones tens of thousands of years old presented enormous technical challenges, since ancient DNA degrades over time and easily becomes contaminated with genetic material from researchers or from bacteria in the surrounding soil. The geneticist Svante Pääbo led the research effort that eventually overcame these challenges, producing a first draft of the full Neanderthal genome in 2010, a landmark achievement recognized with the Nobel Prize in Physiology or Medicine in 2022, turning questions that had previously relied entirely on the shape of bones and stones into questions that could be tested directly against genetic evidence. A separate and striking discovery has added further weight to the case for genuine Neanderthal sophistication. Deep within Bruniquel Cave in southern France, far beyond the reach of any daylight, researchers found ring-shaped structures built from broken stalagmites, deliberately arranged into low, roughly circular walls, some of them showing traces of fire. Dated to around 176,000 years ago, tens of thousands of years before Homo sapiens is known to have reached this part of Europe, these structures could only have been the work of Neanderthals. Reaching this location deep underground would have required a reliable source of portable light, careful navigation through total darkness, and a coordinated group effort to gather, transport, and arrange a substantial quantity of broken stalagmite pieces, activity that speaks to a level of planning, organization, and perhaps ritual or social purpose difficult to reconcile with the outdated image of Neanderthals as simple, purely survival-focused creatures. A skeleton recovered from Shanidar Cave in northern Iraq offers some of the clearest evidence available for a different, quieter kind of Neanderthal sophistication, sustained care for the injured and disabled. The individual, known as Shanidar I, lived to what would have been an advanced age for this period, likely somewhere in his 40s or 50s, despite bearing injuries that would have left him severely impaired for years, possibly decades, before his death. His right arm shows evidence of amputation or a severe injury well below the elbow, healed over long before death. His skull shows damage consistent with partial blindness on one side, and his skeleton shows signs of significant hearing loss as well. An individual with this combination of impairments in a hunting and foraging society would have struggled to contribute fully to gathering food, defending against predators, or traveling long distances unassisted, yet he survived for years after these injuries occurred, evidence that his community continued to feed, shelter, and support him long after he could no longer fully support himself, a pattern consistent with sustained social care within his group. Evidence has also emerged suggesting Neanderthals engaged in symbolic behavior once thought unique to Homo sapiens. Pigments, especially a mineral called ochre, appear at Neanderthal sites in contexts suggesting use for decoration or symbolic marking. In a cave in Spain, a set of geometric engravings on a rock surface, along with shells that appear to have been deliberately pierced and pigmented, has been dated to a period before Homo sapiens is known to have reached that region. This implies independent development of at least some symbolic behavior among Neanderthals, rather than something learned entirely from contact with modern humans, though this particular claim remains actively discussed among researchers, given the difficulty of dating cave art with full confidence. Picture one of these Neanderthal groups moving through a river valley in what is now southern France, somewhere near the close of a long winter. Snow still clings to the higher ground, but the valley floor has begun to soften, and small herds of reindeer are drifting back through the melting undergrowth. A group of a dozen or so individuals, several generations together, follows a familiar route between a cave shelter and a stretch of river shallow enough to cross safely. Someone carries a stone caul, already partly shaped, saved from the last visit to a favored outcrop, about 2 days' walk away. By evening, a fire is burning near the cave mouth, and the group settles in for the night, much as their parents and grandparents had in the same valley through hundreds of winters before this one. Neanderthals were not the only archaic human population living in Asia during this broad period. In 2010, genetic material extracted from a small fingerbone fragment discovered in Denisova Cave in Siberia revealed the existence of an entirely distinct human population, now known as the Denisovans, a group known almost entirely through genetic evidence rather than a rich fossil record. Since only a small number of bone fragments and teeth have been confidently attributed to them so far, genetic comparisons suggest Denisovans shared a common ancestor with Neanderthals more recently than either group shared one with Homo sapiens, meaning the Neanderthal and Denisovan lineages split from each other sometime after both had already diverged from the ancestors of modern humans. Despite this scarcity of physical remains, genetic evidence indicates Denisovans ranged across a broad swath of Asia and left a detectable genetic legacy in several modern human populations. A recently identified jawbone from the Tibetan Plateau, dated to at least 160,000 years ago, suggests Denisovans had already adapted to high altitude, living long before Homo sapiens arrived in the region. A gene variant connected to efficient oxygen use at high altitude, found in some modern Tibetan populations, appears to have been inherited from Denisovan ancestors, a striking example of how interbreeding between different human species left practical, lasting effects on the populations that followed. Denisova Cave itself, the single site responsible for almost everything currently known about this population, has produced one especially remarkable find: a bone fragment belonging to a girl who lived around 90,000 years ago. Her genome revealed she had a Neanderthal mother and a Denisovan father, direct physical evidence of interbreeding between these two distinct human populations occurring within a single family, rather than simply inferred from broader population-level genetic patterns. Discoveries of this kind suggest that encounters between different human species, whatever their frequency, were not always distant or impersonal, and that at least some individuals lived their lives with parents belonging to two entirely different branches of the wider human family tree. While Neanderthals were adapting to the cold landscapes of Europe and Denisovans were spreading across Asia, a separate population in Africa was following its own path. This population would eventually become Homo sapiens, the species that includes every person alive today. For a long time, researchers placed the origin of this species at around 200,000 years ago, based on fossils from Ethiopia. More recent discoveries have pushed that estimate earlier. In 2017, researchers reported on fossils from a site called Jebel Irhoud in Morocco, dated to around 300,000 years ago. These fossils show a face similar in overall shape to that of modern humans, paired with a brain case that remains somewhat more elongated, closer to older hominin forms. This combination suggests that key facial features associated with our species appeared before the brain had finished settling into its fully modern shape. Human evolution did not proceed as a single, coordinated package of changes arriving all at once. Other African sites add further detail to this picture. Fossils from Omo Kibish in Ethiopia. Originally dated to around 195,000 years ago and more recently revised to closer to 230,000 years, show a skull with a fully modern, rounded brain case, though the face is less completely preserved than at Jebel Irhoud. Nearby, at Hurto, fossils dated to around 160,000 years ago show a similar combination of modern and slightly archaic features and include cut marks on the bones themselves, hinting at mortuary practices whose exact meaning remains difficult to interpret with confidence. Taken alongside Jebel Ehud, these Eastern and Northern African sites suggest that the anatomical features defining Homo sapiens did not appear at a single moment in a single place, but assembled gradually across a broad stretch of the African continent over more than 100,000 years. The picture emerging from sites like Jebel Ehud, along with genetic evidence gathered from living populations across the African continent, points away from a single, isolated birthplace for Homo sapiens. Instead, many researchers now favor a model sometimes called African multi-regionalism, in which early Homo sapiens features developed across several regions of Africa somewhat independently, with periodic contact and interbreeding between these regional populations gradually blending their traits into the more unified pattern, eventually recognizable as our species. This stands in contrast to an older assumption of a single small founding population in one specific location, though the full details of this process remain under active investigation. Anatomically, early Homo sapiens can be distinguished from Neanderthals and other archaic humans by several features. A high, rounded skull with a more vertical forehead, a smaller, less projecting brow ridge, a distinct chin, a feature absent or only weakly developed in earlier hominins, a lighter overall skeletal build, less robust than that of Neanderthals living in the same general period. These changes accumulated gradually across hundreds of thousands of years, and early Homo sapiens fossils show a mix of modern and more archaic features rather than a clean, sudden break from earlier forms. The chin, though a small and easily overlooked feature, has attracted considerable attention from researchers precisely because its function remains unclear. Unlike the brow ridge, which plausibly reinforces the skull against the mechanical stress of a powerful bite, or the rounded brain case, which relates directly to the size and shape of the brain it houses, the chin does not obviously strengthen the jaw or serve any clear mechanical purpose related to chewing or speech. Some researchers have proposed it may be a simple side effect of the lower face growing smaller relative to the rest of the skull over the course of human evolution, with the chin left behind as a kind of structural remainder rather than a feature actively selected for its own sake. Others have proposed a role in facial display or attractiveness, a visible marker of individual identity in a highly social species that relies heavily on reading subtle differences in the human face. No explanation has gained clear, decisive support, and the humble chin remains, somewhat fittingly, one of the more mysterious features on an otherwise well-studied modern human skull. For much of the period between 300,000 and roughly 100,000 years ago, Homo sapiens remained largely confined to Africa, though the continent itself offered an enormous range of environments, from dense tropical forest to arid desert margins, each presenting its own particular challenges and opportunities. Archaeological sites from this period show a slow accumulation of behavioral changes, more varied and refined stone tool technology, increasing use of pigments such as ochre, and the appearance of shell beads that appear to have been deliberately perforated and strung, likely for personal ornamentation. This period of African prehistory includes two especially distinctive stone tool traditions known as Still Bay and Howison's Port, both identified primarily from sites along the southern African coast. Still Bay tools, dated to around 71,000 years ago, include finely worked bifacial points shaped with real symmetry and craftsmanship. Howison's port tools, appearing somewhat later, show a shift towards smaller, more standardized blades, an early forerunner of the microlith technology that would become widespread tens of thousands of years later. What makes these traditions especially interesting is their apparent brevity. Each seems to have lasted only a few thousand years before disappearing from the archaeological record, replaced by simpler, more generalized toolkits, before something resembling the earlier, more refined approach eventually reappeared. Some researchers have connected this pattern of appearance and disappearance to fluctuating population size. Since smaller, more isolated populations may struggle to maintain complex cultural knowledge across generations without enough people in regular contact to pass skills along reliably, a dynamic sometimes called the demographic model of cultural transmission. A dramatic event around this same general period has attracted considerable attention, though its actual impact on human populations remains uncertain. Around 74,000 years ago, the Toba volcano on the island of Sumatra produced one of the largest volcanic eruptions of the past 2 million years, releasing enough ash and sulfur into the atmosphere to plausibly cause several years of global cooling. Some researchers have proposed that this eruption caused a severe population bottleneck among early Homo sapiens, sharply reducing numbers and leaving a genetic signature still detectable in living populations today. Other researchers, examining archaeological sites in Africa and India that span the period before and after the eruption, have found no clear evidence of the population collapse this theory would predict, arguing instead that human populations in these regions continued much as before, apparently weathering the eruption's effects without catastrophic consequence. This disagreement remains unresolved. Dramatic natural events do not always leave the dramatic mark on the archaeological and genetic record that their scale might suggest. Blombos Cave, on the southern coast of South Africa, is among the best studied sites from this period, with evidence dating to around 100,000 years ago. This includes engraved pieces of ochre marked with deliberate geometric patterns, along with a set of tools that appear to have been used for mixing and storing a pigment-based substance, possibly for use in decoration or symbolic communication. Evidence of this kind, showing clear intention and planning beyond immediate survival needs, forms much of the basis for what researchers describe as behavioral modernity. This is a loosely defined but widely used term for the set of cognitive and cultural capacities, including symbolic thought, complex planning, and likely language, that distinguish Homo sapiens from earlier hominins. Small marine shells, belonging to a genus called Nassarius, offer some of the oldest known evidence for personal ornamentation anywhere in the world, found at sites across both North Africa and South Africa, and dated to as early as 75,000 years ago in some cases. These shells show small, deliberately made perforations positioned in a way consistent with stringing them together, likely worn as a necklace or bracelet. Many show wear patterns and residual traces of red ochre consistent with prolonged use and repeated handling. The shells themselves were sometimes carried well inland from the coastline where they originated, in some cases over 100 kilometers, indicating that these small ornaments held enough value to be deliberately transported and likely exchanged across a meaningful distance. Another early thread in a long tradition of investing everyday objects with symbolic and social meaning, well beyond their basic material worth. Imagine a woman at Blombos Cave, seated near the entrance in the low afternoon light, working a small lump of ochre against a flat stone. She is not the first in her family to do this. The pattern she scratches into the softened surface, a simple crosshatch of shallow lines, echoes ones her mother taught her, which in turn echo others older still. Nearby, a child threads shells onto a length of plant fiber, copying the careful, unhurried motions of the adults around the fire. None of this feeds anyone or builds anything that will keep out the rain. It exists for its own sake. And that, as much as any stone tool, is what marks this moment as something new in the long story of this family's ancestors. The question of when and how language itself emerged remains one of the most difficult in this entire field, since speech leaves no direct fossil trace. Researchers have looked instead to indirect evidence. This includes the shape of the vocal tract as reconstructed from skull anatomy, the structure of a small bone in the throat called the hyoid, the complexity of behavior, such as coordinated hunting or long-distance trade in raw materials, that would plausibly have required some form of shared, structured communication to organize. Some researchers argue for a fairly early origin of basic language capacity, perhaps shared in some form with Neanderthals. Others argue for a later, more sudden emergence of fully modern language, specifically within Homo sapiens, closely tied to the broader package of behavioral changes appearing in the archaeological record from around 100,000 years ago onward. Given the nature of the evidence, this question may never be fully resolved, and it remains an area where reasonable researchers continue to disagree. This broader question of whether behavioral modernity arrived suddenly or accumulated gradually has itself been the subject of extended debate within the field. An older view, sometimes called the human revolution model, proposed a fairly rapid, coordinated burst of new behavior, including art, elaborate burial, and long-distance exchange, appearing across Homo sapiens populations around 50,000 years ago, possibly linked to some underlying genetic or cognitive change in the brain itself. As evidence from African sites such as Blombos Cave and the Still Bay and Howison's port traditions has accumulated, this sudden revolution model has lost ground to a more gradualist alternative in which the individual components of behavioral modernity, symbolic marking, personal ornamentation, refined toolmaking, appear at different times, in different regions, stretching back gradually over a period of well over 100,000 years, rather than arriving together in one coordinated package. Most researchers working in this field today favor some version of this gradualist picture, though the exact pace and pattern of this accumulation and the precise role of language within it remain active subjects of ongoing research. A separate and more physical thread of change was unfolding alongside this behavioral shift, a gradual softening of the skeleton itself, especially visible in the skull. Comparing Homo sapiens skulls from 100,000 years ago to those from 10,000 years ago and to skulls today reveals a steady reduction in the size of the brow ridge and an overall lighter, less robust bone structure, a trend some researchers link to changing hormone levels, especially testosterone, across the course of human evolution. One hypothesis sometimes called the self-domestication idea, proposes that Homo sapiens populations gradually selected, likely unconsciously, for greater social tolerance and reduced aggression over many thousands of years, favoring individuals better able to cooperate within larger, more complex social groups, and that this shift left a visible trace on the skeleton. Similar in kind to the softened, less robust features seen in many domesticated animals compared to their wild ancestors. This idea remains a hypothesis rather than an established fact. It offers one possible physical echo of the same broader pattern seen throughout this history: increasingly complex social behavior reshaping the human body in ways not directly related to survival tasks like hunting or tool-making alone. By around 70 to 60,000 years ago, groups of Homo sapiens had begun moving out of Africa in numbers substantial enough to leave a lasting genetic and archaeological signature across the rest of the world. This was not the first such movement. Fossil evidence from sites in Israel, including Shkul and Katzeh, shows Homo sapiens present in the Levant as early as 120,000 years ago. A partial skull from a cave in Greece, known as Apodema I, and controversially dated to more than 200,000 years ago, has been proposed by some researchers as evidence of an even earlier, extremely short-lived dispersal into Europe, though this dating and interpretation remains disputed among specialists who have re-examined the fragmentary remains. Genetic evidence suggests these earlier populations did not leave a large, lasting genetic footprint in living humans outside Africa, and may have died out or been absorbed back into surrounding populations. The migration beginning around 60,000 years ago proved different. It became the wave that would eventually reach every inhabited continent. Somewhere on that route, a coastal band might have paused for a season at the edge of the Red Sea, watching the tide expose wide flats of shellfish each morning before the water crept back in. Older members of the group would remember a similar shoreline further south, and the younger ones would learn by simply watching and copying which rocks held the best mussels and which pools were safe to wade at low tide. Whether this particular group ever moved on, or whether their descendants stayed along this same coast for generations, is something no fossil can answer. What can be said is that thousands of small decisions like this one, repeated across scattered families over tens of thousands of years, are what eventually carried a single African population to every corner of the inhabited world. Why this particular migration succeeded where earlier movements had not remains debated. Climate shifts opened and closed potential routes out of Africa at different points. A wetter period across parts of the Sahara and the Arabian Peninsula may have made the journey easier at certain moments than others. Some researchers point to gradual improvements in tool technology and social organization, allowing these later populations to adapt more effectively to the unfamiliar environments they encountered along the way. The Sahara itself has not always been the vast, forbidding desert familiar today. Over hundreds of thousands of years, shifts in the same orbital cycles responsible for the broader pattern of glacial and interglacial periods periodically strengthened the West African monsoon, transforming the Sahara into a landscape of grassland, lakes, and rivers capable of supporting both animal and human populations. These so-called Green Sahara periods opened and closed repeatedly across the time frame relevant to human dispersal out of Africa, alternately providing a viable corridor northward. And then, as conditions reversed, cutting that same route off behind a returning wall of desert. Rock art found across the now arid Sahara, showing herds of cattle, giraffes, hippopotamuses, and swimming figures in a landscape now without any permanent water for hundreds of kilometers in any direction, offers a striking visual record of just how different this region once looked, and how directly its changing climate shaped the routes available to human populations moving through or around it. One proposed route out of Africa follows the southern coastline, along the Arabian Peninsula and then the shores of South Asia, allowing populations to spread rapidly by exploiting the predictable, relatively rich food resources available along a coastline, including shellfish, fish, and stranded marine mammals. Genetic evidence from populations across South Asia, Southeast Asia, and Australia shows a pattern broadly consistent with this kind of rapid coastal expansion, though the details remain difficult to confirm directly, since much of the ancient coastline itself now lies submerged beneath water that rose significantly as the last ice age ended and its ice sheets melted. As these populations spread into new latitudes and new light environments, their bodies gradually adapted in visible ways. Skin pigmentation offers one of the clearest examples. Populations remaining in or near equatorial Africa retained high levels of melanin, offering protection against intense ultraviolet radiation. Populations moving into higher latitudes with weaker and more seasonal sunlight gradually evolved lighter skin, a change that appears to have occurred independently through different genetic mutations in the ancestors of modern Europeans and the ancestors of modern East Asians. Lighter skin allows more ultraviolet light to reach the deeper layers of skin, supporting the production of vitamin D in environments where sunlight is too weak or infrequent for darker skin to produce sufficient amounts. A clear example of natural selection acting on a visible human trait within a relatively short evolutionary timeframe. In some cases, within the past few tens of thousands of years. Overall body shape shifted in response to climate as well, following patterns observed across many warm-blooded animal species and generally known by the names of the naturalists who first described them. Populations adapted to colder climates tend, on average, towards shorter, stockier body proportions, which reduce the ratio of surface area to body volume and help retain heat. Populations adapted to hot, often arid climates tend toward taller, more slender proportions, with longer limbs that increase surface area relative to volume, helping the body shed excess heat more efficiently. These patterns appear, in broad strokes, across populations native to different regions of the world, though individual variation within any single population remains far greater than the average difference between populations, and modern nutrition, migration, and mixing between populations have blurred these patterns significantly compared to the more geographically isolated populations of earlier prehistory. As Homo sapiens spread across Asia and eventually into Europe, they encountered populations that were not entirely unfamiliar. Neanderthals in the west, Denisovans further east, and quite possibly other, less well-documented archaic groups in between. These encounters were not purely cultural. Genetic evidence, drawn from the full sequencing of Neanderthal and Denisovan genomes over the past 2 decades, shows clear evidence of interbreeding between these groups and the incoming Homo sapiens populations. Fossil evidence from East Asia adds further complexity to the timing of this expansion. A cave site called Jirandong in southern China has produced a jawbone with a mix of modern and more archaic features dated to around 100,000 years ago. Remains from Tianyuan Cave near Beijing, dated to around 40,000 years ago, show clearly modern anatomy alongside a genetic profile that connects this individual to both ancient Asian and ancient European populations. Sites like these suggest that the process of Homo sapiens settling across Asia was neither instantaneous nor perfectly uniform, involving multiple population movements over tens of thousands of years, some of which may have left only a limited genetic trace in the populations living in the same regions today. Genetic analysis has also turned up hints of encounters with archaic human populations that have left no confirmed fossil trace at all. Certain patterns of genetic variation in some modern African and Asian populations suggest additional interbreeding events with unidentified hominin lineages, sometimes called ghost populations, since their existence is inferred purely from statistical patterns in modern DNA rather than from any recovered bone or tooth. Whatever these lineages turn out to be, their presence confirms that the fossil evidence recovered so far, however rich it may seem, almost certainly represents only a partial sample of the human family tree. Much of this genetic picture relies on a method researchers call the molecular clock, based on the fact that small genetic mutations accumulate at a roughly steady rate across generations. This lets researchers compare the DNA of two populations and estimate how long ago they shared a common ancestor. Applying this method to a piece of DNA passed down only through the maternal line, researchers identified a most recent common ancestor for all such lineages found in living humans today. An individual who lived in Africa somewhere between 150 and 200,000 years ago, informally nicknamed Mitochondrial Eve. The nickname invites misunderstanding. This was not the only woman alive at the time, nor humanity's sole ancestor. Simply the most recent woman from whom every living person's maternal line can be traced without interruption, with countless other lineages from the same population having died out or ended in daughters only over the many generations since. It can help, after a stretch like this, to step back from the laboratory and picture the people themselves. A Homo sapiens band moving through the hills of the eastern Mediterranean, perhaps 30 or 40,000 years ago, would have known nothing of genomes or molecular clocks. What they would have known was which valleys held reliable water in a dry year, which neighboring group could be trusted to trade obsidian for hides, and which stories, passed down from grandparents, explained the shape of a distant mountain or the reason a particular spring never ran dry. The science reconstructs their movements from a great distance. Their own experience of those same journeys would have been made almost entirely of small, immediate concerns like these. Most people with ancestry outside Africa carry a small percentage of Neanderthal DNA today, typically between 1 and 2% of their total genome, a legacy of interbreeding events that occurred as modern humans and Neanderthals shared the same landscapes for thousands of years. Populations across parts of Asia and Oceania carry a detectable amount of Denisovan ancestry as well, with some populations in Papua New Guinea and other parts of Melanesia showing the highest known levels, in some cases reaching 4 to 6% of their total genome. This inherited genetic material was not simply passive baggage carried forward through the generations. Specific, Neanderthal-derived gene variants appear to have influenced immune system function in modern humans, potentially offering some benefit in fighting off pathogens already present in Eurasia when Homo sapiens arrived from Africa. Other inherited variants have been linked to skin and hair characteristics, and more ambiguously, to certain health outcomes in modern populations, including altered risk for some autoimmune conditions. The picture that emerges is one of genuine biological exchange between different human species, not a simple story of one species replacing another without any lasting trace. Neanderthals themselves disappeared from the fossil record by around 40,000 years ago, with some of the last known populations surviving in refuges in what is now Spain and Gibraltar. The causes of this disappearance remain debated, and no single explanation has gained universal acceptance among researchers. Competition with incoming Homo sapiens populations for shared resources is one commonly proposed factor. Climate instability during this period, marked by rapid and sometimes severe swings in temperature, may have placed additional strain on already small and scattered Neanderthal populations. Some researchers have proposed that Neanderthal populations were simply too small and too thinly spread to remain genetically viable over the long term, making eventual extinction likely even without direct competition from another species. The truth may involve some combination of all these factors, playing out differently in different regions across a period of several thousand years, rather than a single sudden event. Denisovans appear to have persisted somewhat longer in parts of Asia, based on genetic evidence suggesting more recent interbreeding events in some regions. The exact timing and circumstances of their disappearance remain far less clear than for Neanderthals, given the very limited physical fossil record available for this population. By the later stages of the late Pleistocene, Homo sapiens had increasingly become the sole surviving human lineage, a gradual shift rather than a single clean boundary, since the exact final dates for Neanderthals, Denisovans, and other archaic populations remain difficult to pin down with full precision. This was a situation that had not existed for millions of years, since multiple hominin species had typically coexisted in one combination or another across the preceding several million years of this history. Even as the sole surviving hominin, Homo sapiens remained, by later standards, impressively scarce across the planet. Estimates of global population size for this period are necessarily rough, built from a combination of genetic diversity studies and the density of known archaeological sites. But most researchers place the total human population at somewhere between a few 100,000 and a few million individuals for much of the Upper Paleolithic, scattered thinly across every inhabited continent. This relatively small population size, maintained across tens of thousands of years, helps explain why genetic diversity among modern humans remains comparatively low compared to some other primate species with far smaller geographic ranges. Since the entire human species descends from a population that, for long stretches of its history, would have fit comfortably within a single modern city district, however widely dispersed those individuals actually were across the surface of the globe. By around 12,000 years ago, at the dawn of agriculture, this pattern had already begun to shift. Estimates for total global population at the start of the Holocene generally fall somewhere in the low millions, still modest by later standards, climbing steadily as farming took hold in one region after another. Agriculture's greatest demographic effect was not a sudden population explosion, but a change in the underlying ceiling on how many people a given area of land could support, allowing populations to grow gradually toward that new, higher ceiling over the following thousands of years. A slow but compounding shift that would eventually support the much larger, denser populations of the first cities. The period following this, roughly 40,000 to 12,000 years ago in Europe, is often called the Upper Paleolithic. It left behind some of the richest and most evocative archaeological evidence in the entire human story. Across this period, Homo sapiens populations in Europe produced cave paintings, carved figurines, elaborate burials, and increasingly sophisticated tools made from bone, antler, and ivory, as well as stone. The cave art of this period remains striking even today. At Chauvet Cave in southern France, dated to around 36,000 years ago, artists painted horses, lions, rhinoceroses, and other animals with a confident, fluid line and a clear understanding of anatomy and movement, using the natural contours of the cave wall to suggest depth and motion. At Lascaux, painted somewhat later, around 17,000 years ago, a similar range of animals appears across a network of connected chambers, executed with techniques including shading and perspective that show real technical sophistication. Imagine the walk into a cave like Chauvet made by firelight, the outside world of wind and open sky falling away behind a narrowing passage of cold stone. The artist carries a small stone lamp, its flame throwing a modest, moving circle of light barely large enough to work by. Progress is slow, feeling along familiar walls toward a chamber visited perhaps only a handful of times before. There is no audience waiting. Whatever is painted here, in this particular darkness, will be seen afterward by very few living eyes. And yet the work is done with evident care all the same, line after line, an act carried out for reasons that likely had little to do with being seen at all. For a long time, this kind of sophisticated figurative art was treated as a largely European phenomenon, closely tied to the Homo sapiens populations settling that continent during the Upper Paleolithic. That picture has shifted significantly following discoveries on the Indonesian island of Sulawesi, where a cave painting depicting a hunting scene involving wild pigs and small human-like figures has been dated to at least 43,000 years ago. A separate painting of a wild pig on its own has been dated to nearly 45,000 years ago, making it, at the time of its dating, among the oldest known figurative artworks anywhere in the world. These Indonesian discoveries suggest that the capacity and inclination for this kind of representational art was not confined to any single region, but had likely already developed within the broader Homo sapiens population before its major migrations had even finished spreading the species across the globe. A recurring and especially personal form of Ice Age art appears across caves on multiple continents. Hand stencils, created by pressing a hand against the cave wall and blowing pigment around it, leaving a negative silhouette behind once the hand was removed. Examples appear at Chauvet and other European sites. Also, once again, in the caves of Sulawesi, where hand stencils have been dated to at least the same broad period as the island's figurative paintings. In India, the rock shelters of Bhimbetka preserve a long, layered sequence of paintings spanning tens of thousands of years, the earliest layers likely dating well back into this same general Ice Age period, continuing in some form up through far more recent history. This recurring impulse to leave a direct physical trace of one's own hand on a cave wall appears across populations with no direct contact with one another, separated by tens of thousands of kilometers and, in some cases, tens of thousands of years. hinting at something close to a universal human inclination toward this particular, deeply personal form of mark-making. The purpose of this art remains a matter of ongoing interpretation. Some researchers have proposed a connection to hunting magic, imagining the paintings as an attempt to influence the success of a coming hunt through symbolic representation. Others suggest a role in initiation rituals, storytelling, or the marking of important gathering sites used across many generations. Much of this art appears in deep caves, often in locations requiring difficult and even dangerous access, involving crawling through narrow passages by the light of a simple lamp. Many researchers suspect the art carried genuine ritual or spiritual significance for this reason, though the precise beliefs behind it are, by their nature, unrecoverable from the physical evidence alone. Burial practices from across this period offer another, complementary window into the inner lives of these populations, even without any written record of their beliefs. Grave goods, including tools, ornaments, and food offerings, appear repeatedly at burial sites across widely separated regions and time periods. These consistent patterns demonstrate deliberate mortuary behavior, treating the dead with intention and care. Though exactly what people believed about death itself is harder to establish from the objects alone. Ochre, the same red mineral pigment used in cave art and personal decoration, appears scattered over human remains at burial sites across Africa, Europe, and Asia, spanning tens of thousands of years. A recurring practice widespread enough to suggest an old and broadly shared association between this particular color and the treatment of the dead, even though the exact meaning attached to it inevitably varied from one community and one era to the next. Alongside cave painting, this period also produced small carved figurines, often depicting the human form with exaggerated features, generally referred to collectively as Venus figurines, despite the varied and sometimes rough style across individual examples. The best known, discovered in what is now Austria and dated to around 25,000 years ago, shows a female figure with pronounced hips, breasts, and abdomen, and no clearly carved face. Interpretations vary widely, ranging from fertility symbolism to self-portraiture, created by women looking down at their own bodies, to broader ideas about beauty, health, or status within these communities. No single interpretation has gained universal acceptance. Music also left physical traces from this period, a form of evidence easy to overlook alongside the more visually striking cave paintings and figurines. Flutes carved from bird bone and mammoth ivory, recovered from caves in what is now southern Germany and dated to around 40,000 years ago, include carefully placed finger holes, evidence of real technical skill, and, presumably, an established musical tradition behind their construction. Producing a working flute from bone requires precise judgment of wall thickness and hole placement, suggesting these instruments were refined over generations rather than invented from nothing by a single maker. Further east, across the open, treeless plains of what is now Ukraine and Russia, some Upper Paleolithic groups built dwellings using the bones and tusks of mammoths, arranged in careful circular patterns and likely covered with hides to form a shelter. Constructing one of these dwellings required the bones of many individual mammoths, whether hunted directly or scavenged from animals that had died of other causes, and represents a striking adaptation to a landscape with little available timber, turning the remains of the largest animals on the steppe into building material for shelter against its harsh, open winters. Some of the earliest physical evidence for counting or record keeping also dates to this broad period. A small bone tool from Border Cave in South Africa, notched with a series of deliberate marks and dated to around 42,000 years ago, may represent an early tally system, a way of recording a quantity, perhaps days, lunar cycles, or some other repeated count, through a simple, cumulative series of physical marks. A similar and better-known example: the Ishango bone, discovered near the headwaters of the Nile and dated to somewhere between 18 and 20,000 years ago, carries groups of notches arranged in patterns that some researchers have interpreted as an early tally system, and others have proposed may reflect a more deliberate mathematical structure, though this stronger interpretation remains contested. Even in its simplest form, as a straightforward tally, this kind of notched bone represents an important cognitive step: the use of a physical, external object to store and communicate information beyond what memory alone could reliably hold, a foundational idea underlying every later system of writing, counting, and record keeping in human history. This period also saw the peopling of Australia, a movement that required deliberate sea crossings even during the lowest sea levels of the last ice age. Australia and New Guinea were joined together at the time into a single landmass called Sahul. This landmass remains separated from the Asian mainland by open water at every point along the route. Archaeological evidence from northern Australia places human arrival at least 65,000 years ago, and possibly earlier. This required some form of seaworthy craft and the willingness to cross open ocean without any land visible on the horizon ahead. A genuine achievement for this period, regardless of how simple or sophisticated the vessels involved may have been. Once established in Australia, human populations spread across the continent and adapted to an exceptional range of environments, from tropical coastline to the driest desert interior. Over tens of thousands of years, Aboriginal Australian societies developed detailed knowledge of local plants, animals, and water sources, along with complex social and ceremonial systems. Some of this knowledge is reflected in oral traditions that researchers believe may preserve genuine memories of events, such as coastal flooding, stretching back thousands of years, passed down through many generations of careful, deliberate storytelling. Elsewhere, human populations continued spreading into new territory as the last ice age approached its coldest point. Around 20,000 years ago, vast ice sheets covered much of northern Europe, Asia, and North America during this period, locking up enormous quantities of water and lowering global sea levels by well over 100 meters compared to today. This exposed a land bridge connecting Siberia and Alaska, a region now known as Beringia, which would eventually serve as a route for the peopling of the Americas. The exact timing and route of the peopling of the Americas remains one of the more actively debated questions in this entire field. For decades, the dominant model held that small groups crossed Beringia on foot, then moved south through an ice-free corridor that opened between two massive ice sheets covering what is now Canada, arriving in the continental United States by around 13,000 years ago. This population, associated with a distinctive stone tool tradition known as Clovis, after a site in New Mexico, was long considered the first successful human presence in the Americas. Clovis points themselves represent a distinctive technological achievement, a finely worked fluted stone spear point with a long channel removed from the base on each face, allowing the point to be securely fastened to a wooden shaft. This fluting technique required considerable skill, since removing a long, thin flake from the base of an already shaped point risked shattering the entire piece at the final, most delicate stage of its production. Clovis points have been found across most of North America, often associated with the remains of mammoths and other now extinct large mammals, suggesting these early populations hunted large, dangerous game as a significant part of their diet, alongside a broader range of smaller animals and plant foods that leave less obvious traces in the archaeological record. More recent archaeological finds have complicated this picture significantly. Sites in South America, including Monteverde in Chile, show credible evidence of human occupation dating to at least 14,500 years ago, predating the opening of the ice-free corridor and challenging the idea that Clovis represented the very first arrival. Some researchers now argue for an earlier coastal migration route, with small groups moving by boat along the Pacific coastline, exploiting rich marine resources and bypassing the interior ice sheets entirely. Evidence for this coastal route is difficult to confirm directly, since much of the relevant ancient coastline now lies underwater, submerged by rising sea levels since the end of the last ice age. But genetic and archaeological clues continue to accumulate in its favor. A striking piece of evidence emerged in 2021 from a site called White Sands in New Mexico. There, researchers identified a series of human footprints preserved in ancient lake sediment, dated using the seeds of an aquatic plant found in the same layers to between 21 and 23,000 years ago, several thousand years before the Clovis tradition and well before the ice-free corridor would have been passable. This dating proved controversial at first, prompting close scrutiny from other researchers, but subsequent studies using different dating methods on the same footprint layers have produced broadly consistent results, lending growing support to the idea that humans reached North America significantly earlier than the traditional Clovis first model allowed. The footprints themselves, apparently left by a mix of adults and children walking across the soft lakeshore mud, offer a strikingly direct, personal trace of this otherwise abstract and heavily debated migration. Whatever the exact route, human populations spread through the Americas with striking speed once established, reaching the southern tip of South America by around 14,000 years ago, based on evidence from sites in Chile and Argentina. Along the way, these populations encountered an enormous range of large mammals, many of them unfamiliar in scale to anything these humans or their immediate ancestors had previously hunted, including mammoths, giant ground sloths, saber-toothed cats, and enormous armored relatives of modern armadillos. Somewhere along a braided river valley in what is now the American Midwest, a small hunting party might have spent an early morning tracking a mammoth herd through frost-covered grass, reading the impressions left in soft mud from the previous night's rain. Success meant meat enough to last the group for weeks, along with hide, bone, and sinew for tools and clothing that would carry them through the coming winter. Failure meant simply moving on to the next herd, the next valley, patience being as essential to this way of life as any spear. Generation by generation, journeys shaped by exactly this kind of patient, opportunistic tracking carried human populations the length of 2 continents in what was, geologically speaking, barely more than a heartbeat. Genetic studies of both ancient and living indigenous American populations have added considerable nuance to this picture over the past 2 decades. Rather than a single uniform wave of migration, the genetic evidence points to at least a few distinct population movements and periods of isolation, including a period during which the founding population appears to have remained genetically separated from other Asian populations for several thousand years, likely somewhere in or near Beringia itself before continuing onward into the Americas. This idea, sometimes called the Beringian standstill hypothesis, would help explain certain genetic patterns that are otherwise difficult to account for through a single, uninterrupted migration. During this proposed standstill period, the population occupying Beringia would have lived on a landscape quite unlike the frozen, largely barren tundra found in the region today. Despite its high latitude and cold winters, Beringia during the last ice age formed part of a broader ecosystem researchers call the Mammoth Steppe, a dry, grassy landscape supporting large herds of grazing animals, including mammoths, horses, bison, and woolly rhinoceroses, sustained by relatively low winter snowfall that left enough vegetation exposed for these animals to graze through the colder months. This productive, if visually stark, landscape would have offered a viable, if demanding, home for a human population waiting out several thousand years before conditions allowed further movement into the Americas, supported by a reliable, if seasonally challenging, supply of large game and the resources that came with it, including bone, hide, and sinew alongside meat itself. The disappearance of many of these large animals, along with a broader wave of megafauna extinctions across multiple continents during the final stages of the last ice age, has produced one of the more persistent debates in this field. One explanation, sometimes called the overkill hypothesis, points to human hunting pressure as the primary cause, arguing that large, slow-reproducing animals with no prior experience of human hunters were especially vulnerable to a newly arrived, skilled predator. A second explanation emphasizes rapid climate change at the end of the Ice Age, as shifting temperature and rainfall patterns transformed the habitats these animals depended on faster than many species could adapt. A third view holds that a combination of both factors, human hunting pressure layered onto an already stressed and shifting environment, likely explains the pattern better than either factor alone. The evidence does not point to a single, uniform answer across every region and every species. In Australia, megafauna extinctions occurred over a long stretch of time following human arrival, making a simple, rapid overkill scenario harder to support in every case. In North America, the timing of many extinctions clusters more closely with both human arrival and a sudden, sharp cold snap known as the Younger Dryas, beginning around 12,900 years ago, leaving the relative contribution of each factor difficult to disentangle with full confidence. One especially telling detail comes from the very last surviving population of woolly mammoths isolated on Wrangel Island off the coast of Siberia after rising sea levels cut the island off from the mainland. This small, genetically isolated population persisted until around 4,000 years ago, well after mainland mammoth populations had already disappeared, at a point in history when the pyramids of Egypt had already been standing for centuries. Genetic analysis of these final Wrangel Island mammoths reveals a population in visible decline, carrying a heavy burden of harmful genetic mutations likely accumulated through generations of inbreeding within such a small, isolated group, suggesting that genetic decay, compounding whatever pressure came from a changing climate, and any occasional human contact played its own role in finally ending a lineage that had otherwise endured for hundreds of thousands of years. As the Ice Age drew to a close, human populations across the world were living in small, mobile groups, generally moving across the landscape in a seasonal rhythm tied to the availability of plants, game, and fresh water. Archaeological evidence from this broad period, spanning tens of thousands of years and every inhabited continent, shows considerable variation in how these groups organized themselves. Some patterns appear widely, if not universally. Groups tended to be small, often numbering in the dozens rather than the hundreds, with larger gatherings occurring periodically when local resources allowed, bringing together several smaller bands for shared ceremonies, trade, and the exchange of marriage partners between otherwise separate groups. Burial practices from this period sometimes show a level of care and material investment that speaks to real social significance placed on certain individuals. At a site called Sungir, in what is now Russia and dated to around 34,000 years ago, 2 children were buried head to head, their bodies covered in thousands of carefully carved ivory beads, evidently sewn onto clothing that has long since decayed, along with ivory spears, animal carvings, and other elaborate grave goods. Producing thousands of individual beads by hand would have required an enormous investment of time and skill. The scale of this particular burial has led some researchers to suggest that certain individuals, even children, could hold inherited status or significance within their community, well before the emergence of settled agricultural societies more commonly associated with formal social hierarchy. Long-distance exchange networks moved materials across surprising distances during this period. Shells from coastal regions have been found hundreds of kilometers inland at sites across Europe and Africa. High-quality stone suitable for toolmaking was sometimes carried or traded across distances of several hundred kilometers from its original source. This kind of exchange required some level of sustained contact between different groups, whether through direct travel, trade chains passing material from group to group, or a combination of both. It points to social networks significantly more extensive than the small, local bands directly visible in the archaeological record at any single site. Obsidian, a naturally occurring volcanic glass prized for producing an unusually sharp cutting edge, offers one of the clearest examples of this kind of long-range exchange, since its source can often be traced to a specific volcanic outcrop through chemical analysis, allowing researchers to map trade routes with real precision. Obsidian from sources in Anatolia has been found at sites hundreds of kilometers away across the Fertile Crescent. Separately, obsidian originating on Mediterranean islands such as Melos, in what is now Greece, appears at sites on the surrounding mainland dated to as early as 14,000 years ago, requiring a sea crossing of open water to reach the island in the first place. Evidence of this kind shows that watercraft capable of navigating open sea, first clearly demonstrated by the far earlier crossings into Australia, remained an active and valuable technology among these later populations as well. Used not only for major continental migrations, but for the more routine business of trade and resource gathering across shorter, though still demanding, stretches of open water. Technology continued advancing steadily through this period as well. Bone and antler needles with tiny eyes, dating to around 40,000 years ago in some sites, point to sewn, fitted clothing rather than simple draped hides. An important development for populations living through the coldest stretches of the Ice Age. Spear throwers, sometimes called atlets, extended the effective range and force of a thrown spear well beyond what an arm alone could achieve. Later still, in some regions, the bow and arrow appeared, offering even greater range, accuracy, and hunting efficiency. Though the exact timing of its earliest use varies by region and remains a topic of ongoing archaeological research. Cordage, simple twisted plant fiber string, represents another technology from this period that rarely survives directly in the archaeological record, since plant fiber decays quickly under most conditions, yet its impact would have been considerable. A fragment of fired clay from Dolní Vykstanice in the Czech Republic, dated to around 28,000 years ago, preserves the impression of woven cordage pressed into the clay before it hardened. This offers rare, indirect evidence for a technology that likely underpinned an enormous range of practical tasks, binding a stone axe head to its wooden handle, constructing snares and nets for catching small game and fish, lashing together the poles of a shelter, or carrying gathered food and firewood back to camp. A technology, this fundamental, quietly present behind so many other tools and practices of daily life, is easy to overlook precisely because it so rarely survives to be found. The archaeological record likely preserves only a fraction of the practical knowledge these populations actually possessed and depended upon. Stone tool technology itself grew steadily more refined across this same broad period, moving towards smaller, more specialized, and more standardized forms known as microliths. Tiny, precisely shaped stone blades, often no larger than a fingernail. Rather than serving as complete tools on their own, microliths were typically set into a wooden or bone shaft, several arranged together in a row and secured with resin or binding, creating a composite tool with a cutting edge that could be repaired piece by piece as individual segments wore down or broke. Rather than discarding an entire tool and starting again from a fresh piece of stone. This modular approach to toolmaking represents a real conceptual advance, breaking a single function down into interchangeable component parts, a way of thinking about technology that would remain useful across every later stage of human history. Among the animals living alongside these late Ice Age human groups, one relationship stands out as especially old and especially close: the domestication of the dog. Genetic evidence points to dogs descending from a now extinct population of wolves, with the domestication process likely beginning somewhere between 20 and 40,000 years ago, well before the beginnings of agriculture, and significantly earlier than the domestication of any other animal. Exactly how this relationship began remains debated. One long-standing idea suggests that wolves less fearful of humans began scavenging near hunting camps and rubbish sites, gradually growing more tolerant of human presence over many generations, with humans in turn favoring the calmer, more useful individuals among them. Whatever its precise origin, the partnership proved durable. Dog remains found buried alongside human remains at several Upper Paleolithic sites suggest these animals had become valued companions, not simply tolerated scavengers, long before any human community had begun planting a single crop. As the last Ice Age drew to its close, around 15,000 to 11,000 years ago, global climate began a broad warming trend, though this warming did not proceed smoothly. A sudden, sharp return to near-glacial conditions, known as the Younger Dryas event, interrupted this general warming for roughly 1,000 years. Temperatures then rose again and settled into the relatively warm, stable climate that has persisted, with only modest variation, for the past 11,000 years or so, a period geologists call the Holocene. This long stretch of unusually stable climate coincides closely with one of the most consequential shifts in the entire human story: the move from foraging for wild food toward the deliberate cultivation of crops and the herding of domesticated animals. This transition did not happen everywhere at once, and it did not happen for the same reasons in every region. Instead, agriculture developed independently in several separate parts of the world over a period spanning several thousand years, pointing towards shared underlying conditions that made this shift possible rather than the spread of a single idea from one original source. One of the earliest and best documented centers of this transition lies in a region often called the Fertile Crescent, an arc of land stretching from the eastern Mediterranean coast through parts of modern Turkey, Syria, Iraq, and Iran. Wild ancestors of wheat and barley grew naturally across parts of this region, alongside wild populations of sheep, goats, and cattle, providing a starting point that later human communities gradually shaped through selective harvesting, planting, and herding. The Natufian culture, present in the Levant from around 15,000 to 12,000 years ago, offers an important window into the period just before formal agriculture began. Natufian communities were still foraging rather than farming, but they were doing so from increasingly permanent or semi-permanent settlements, harvesting wild cereals with specialized sickle blades and storing surplus food for leaner periods. This kind of settled, resource-intensive foraging appears to have set the stage for the deliberate cultivation that followed, blurring the boundary between simply gathering wild plants and actively managing them. Picture a Natufian household in early summer. The hillsides around their settlement pale gold with ripening wild wheat. A woman moves through the grass with a sickle set with sharp flint teeth, cutting stalks with practiced, economical strokes, while behind her a line of children gathers the fallen heads into woven baskets. By evening, the day's harvest will be spread to dry on flat stones near the houses, and some portion of it stored away in a pit lined with clay, insurance against a poor season still months off. None of this yet counts as farming in the fullest sense. No one has deliberately planted these particular plants. But the rhythm of this work, tied to a fixed place and a returning season, is already very close to what farming would soon become. Natufian burial sites offer further insight into this transitional world. At a site in northern Israel, archaeologists uncovered the grave of an elderly woman, dated to around 12,000 years ago, buried alongside dozens of tortoise shells and the remains of a wild boar, a golden eagle, other unusual animal offerings in what researchers have interpreted as the grave of a shaman or a similarly significant ritual figure within her community. Burials of this kind, invested with unusual care and unusual grave goods, suggest that even before the earliest crops were deliberately sown, Natufian society had already developed meaningful social distinctions and specialized religious or ceremonial roles, foreshadowing the more elaborate social hierarchies that would become increasingly visible once farming took hold. A striking site connected to this broader transition is Göbekli Tepe in what is now southeastern Turkey, dated to around 11,600 years ago, before clear evidence of full agriculture appears in the surrounding region. The site consists of large carved stone pillars, some standing several meters tall and decorated with detailed animal reliefs, arranged in circular enclosures. Building and maintaining a site of this scale would have required significant organized labor, coordinated across a group larger than a typical small foraging band, raising interesting questions about the relationship between social organization, ritual life, and the eventual shift towards settled agriculture in this particular region. Göbekli Tepe's builders, based on animal bones and plant remains recovered at the site, were still foraging and hunting wild game rather than farming, which has led some researchers to propose an idea running somewhat against the traditional order of this story, that the demands of gathering, feeding, and organizing large groups of people for periodic construction and ritual activity at a site like this may have helped drive the eventual move toward more intensive food production rather than agriculture, simply developing first and monumental construction following afterward as a later luxury. Genetic studies of modern wheat varieties, meanwhile, have traced the origin of domesticated einkorn wheat to wild populations growing in the hills of the Karakadank mountain range, not far from Göbekli Tepe itself, adding an intriguing local connection between this monumental ritual site and the wider agricultural transformation of the surrounding region. Why foraging populations in several parts of the world eventually shifted toward farming remains a debated question. Farming, at least in its early stages, often required more total labor than foraging for a comparable amount of food. Early farming populations frequently show signs of poorer health in their skeletal remains compared to foraging populations from the same general region, including shorter average stature and more frequent dental problems linked to a diet increasingly dominated by starchy cereal grains. Several explanations have been proposed for this apparent trade-off. Population pressure is one commonly cited factor. Since a growing population in a region with limited wild food resources may have needed to intensify food production simply to keep pace, even if the resulting lifestyle was, in some respects, more demanding than what came before. Climate stability during the early Holocene may have played a role as well, since reliable, predictable seasons make it significantly easier to plan around the multi-month cycle required for planting and harvesting a crop, a much riskier undertaking during the more volatile climate of the preceding ice age. Some researchers also point to social and political factors. Agriculture allowed for the accumulation and storage of surplus food in ways foraging generally did not, creating new possibilities for social stratification, inherited wealth, and organized leadership. This may have appealed to certain individuals or groups within a community, even if the broader population did not necessarily benefit in terms of health or leisure time. Whatever the precise mix of causes, the archaeological evidence shows a genuine transition taking place across the Fertile Crescent between roughly 11,500 and 9,000 years ago. Wild cereal grains gradually gave way to domesticated varieties, distinguishable in the archaeological record by physical changes such as a tougher stalk that no longer shatters and scatters its seeds naturally, a trait humans would have selected for without necessarily understanding the underlying genetics, simply by continuing to plant and harvest the seeds from whichever plants proved easiest to gather. This process, often called unconscious selection, worked through a simple and almost accidental logic. In a wild cereal population, most seed heads shatter easily, scattering their seeds onto the ground as soon as they ripen, an effective strategy for a wild plant reproducing on its own. A small number of plants, due to natural genetic variation, carry a mutation that keeps their seed heads intact rather than shattering. Under purely wild conditions, this mutation offers little advantage, and may even be a disadvantage, since the seeds are not released to spread and germinate. Once humans began deliberately harvesting grain with a sickle, however, the plants most likely to be successfully cut and gathered, rather than losing their seeds to the ground beforehand, were precisely these non-shattering individuals. If some of this harvested grain was then replanted, whether deliberately or simply through spillage near a settlement, the next generation would contain a higher proportion of the non-shattering trait than the wild population it came from. Repeated over many growing seasons, this simple, self-reinforcing cycle could transform a population of wild cereal into a recognizably domesticated crop within a few hundred years, without any farmer needing to understand genetics or even necessarily intending to create a new, permanently altered variety of plant at all. Animal domestication followed a broadly similar pattern of gradual, unintentional selection. Sheep and goats were likely among the earliest domesticated animals, herded initially perhaps for meat and only later valued for milk, wool, and other secondary products. Cattle and pigs followed within a few thousand years. Each domestication event involved a long process of genetic change, as animals more tolerant of human presence, easier to manage, and more productive under human care were, generation after generation, more likely to survive and reproduce within a managed herd. Cats followed a markedly different path toward domestication compared to dogs, sheep, goats, or cattle. Rather than being actively herded or bred for a specific practical purpose, wild cats appear to have drawn closer to human settlements largely on their own initiative, attracted by the rodents that gathered around stored grain once farming communities began accumulating surplus food worth protecting. This more self-directed relationship, sometimes described as self-domestication, likely began in the Fertile Crescent alongside the earliest grain agriculture, evidenced by a cat burial found alongside a human grave on the island of Cyprus, dated to around 9,500 years ago. Well before cats could have reached this island without deliberate human transport. Unlike dogs, whose behavior and even physical appearance changed dramatically through many thousands of years of deliberate breeding, domestic cats today remain genetically and behaviorally quite close to their wild ancestors, a domestication process that proceeded largely through the cat's own initiative rather than sustained human direction. This process altered domesticated animals in ways that extended well beyond simple tameness. Compared to their wild ancestors, many domesticated species show smaller brains relative to body size, altered coat colors and patterns, and changes to reproductive cycles, including a loss of strict seasonal breeding in some species, allowing offspring to be produced across a wider portion of the year. Some researchers connect this consistent cluster of traits, appearing across many unrelated domesticated species, to changes in a shared set of cells during early embryonic development, a hypothesis that remains an active area of biological research rather than a fully settled explanation. Whatever its underlying cause, this pattern shows up clearly enough across sheep, goats, cattle, pigs, and dogs alike that researchers have given it a name: domestication syndrome, treating it as a recognizable biological signature of animals that have spent many generations living closely alongside humans. Agriculture did not emerge only in the Fertile Crescent. In China, rice cultivation developed independently along the Yangtze River region, with millet cultivation developing somewhat separately in the drier lands further north. Both processes underway by around 9,000 years ago. In Mesoamerica, maize was gradually domesticated from a wild grass called teosinte, a transformation involving especially dramatic changes in plant structure, beginning perhaps as early as 9,000 years ago and continuing to develop over several following millennia. In parts of New Guinea, root crops such as taro were cultivated independently as well, in a wet, tropical environment quite different from the drier landscapes associated with cereal farming elsewhere. Africa produced its own independent centers of domestication as well, though somewhat later than the Fertile Crescent. In the Sahel region, south of the Sahara, sorghum and pearl millet were domesticated from local wild grasses, crops well suited to the region's hot, seasonally dry climate, in a process likely underway by around 4,000 to 5,000 years ago. In the Andes Mountains of South America, potatoes were domesticated from wild tuber-bearing relatives at high altitude, alongside quinoa and other crops adapted to the thin air and cold nights of this challenging environment. While llamas and alpacas became the primary domesticated animals of the region, filling a role broadly similar to sheep, goats, and cattle elsewhere. Across the whole planet, this pattern of scattered, independent invention rather than a single point of origin gradually spreading outward appears to be the rule for agriculture rather than the exception. These separate, independent origins of agriculture, emerging in different regions without direct contact between them, suggest that similar underlying pressures were at work across multiple parts of the world during this same general period of post-Ice Age climate stability. Rather than a single invention spreading outward from one origin point, agriculture appears to have been an idea, perhaps a set of related solutions that human populations in several separate regions arrived at independently once the climate and other local conditions made it a viable option. Once established, farming brought consequences that extended well beyond diet alone. Settled village life allowed for larger, more concentrated populations than mobile foraging typically supported, since a fixed area of farmed land could feed significantly more people than the same area of wild landscape exploited through foraging. Villages grew into larger settlements, and within a few thousand years, some of these settlements had grown into the first true cities. With populations in the thousands, organized systems of governance, increasingly specialized labor, as not every member of these larger communities needed to be directly involved in producing food. Skeletal remains from early farming communities also preserve a physical record of the changing demands placed on the human body during this transition. Bones from early farmers frequently show wear patterns and joint changes consistent with repetitive, physically demanding labor, including grinding grain by hand for extended periods, a task that shows up clearly in the arm and shoulder bones of many early agricultural skeletons. Dental wear caused by the fine grit inevitably mixed into flour ground using stone tools adds further evidence of this same shift. Studies comparing the skeletons of foraging populations to farming populations from the same general region consistently find that early farmers show reduced bone density and altered limb proportions compared to their foraging counterparts. These changes are generally interpreted as reflecting a less varied, more repetitive daily workload, concentrated around a narrower set of physically demanding tasks tied directly to cultivating and processing a small number of staple crops. This contrasts with the more physically varied demands of a mobile foraging lifestyle, spent moving across a changing landscape in pursuit of a broader range of wild foods. This shift also brought new challenges. Living in close, permanent proximity to domesticated animals exposed human populations to a range of new diseases that had previously circulated mainly among animal populations. Since many infectious diseases affecting humans today, including measles, influenza, and tuberculosis, appear to have originated as diseases of domesticated livestock before adapting to spread between humans as well. Denser populations, combined with less varied diets and closer contact with stored grain that could attract pests, likely made these communities more vulnerable to both infectious disease and periodic famine than smaller, more mobile foraging groups had generally been. Agriculture also left a visible mark on the human genome itself, through the spread of a genetic trait called lactase persistence, the ability to continue digesting the milk sugar lactose comfortably into adulthood. In most mammals, and in most human populations without a long history of dairying, the ability to digest lactose fades after early childhood. Among populations with a long history of herding cattle, sheep, or goats for milk, however, a genetic mutation allowing lactase production to continue throughout life spread rapidly under strong selective pressure. Since the ability to safely consume milk as an adult offered a valuable, reliable source of nutrition in societies that depended heavily on their herds. This particular mutation appears to have arisen independently in different herding populations across Europe, the Middle East, and parts of Africa. Another example of agriculture reshaping human biology directly, on a timescale of thousands rather than millions of years. Social organization changed as well. The accumulation of stored surplus food created something that had rarely existed in earlier hunting and gathering. Societies, significant, storable, inheritable wealth. Archaeological evidence from early farming settlements increasingly shows differences in house size, burial goods, other markers of status between individuals and families, suggesting the gradual emergence of social hierarchy in a way that appears less pronounced, though not entirely absent, in the archaeological record of earlier foraging societies. Studies of surviving hunter-gatherer societies in the modern era, while not a perfect stand-in for prehistoric populations, offer some insight into why this shift toward inherited wealth and hierarchy was significant. Many mobile foraging societies studied by anthropologists over the past century show strong social norms actively discouraging the accumulation of personal wealth or status, including customs requiring successful hunters to share meat widely across the group regardless of who made the kill, and social mechanisms, ranging from gentle teasing to more serious social pressure, aimed squarely at anyone seen as too boastful or too eager to accumulate more than their share. Food that spoils quickly and cannot easily be stored, along with a highly mobile lifestyle that limits how much any individual can carry or defend, likely made this kind of enforced sharing a practical necessity as much as a moral preference. Once farming allowed food to be stored for long periods and defended within a fixed, permanent settlement, the practical basis for this kind of enforced equality weakened significantly. Removing a check on individual accumulation that had likely shaped human social life for the entire preceding stretch of this history. None of these changes happened as a sudden, complete break from the past. For thousands of years following the earliest agricultural experiments, farming and foraging coexisted, sometimes within the same region, sometimes even within the same community, as people gradually adjusted their reliance on cultivated crops relative to wild food sources. Some populations, especially in environments less suited to cereal farming, continued foraging as their primary way of life for thousands of years after agriculture had taken hold elsewhere. And a number of foraging societies persisted, in various forms, into the modern era. Çatalhöyük, a well-studied early settlement in central Turkey, occupied from around 9,400 to 7,000 years ago, offers a detailed picture of daily life during this transitional period. Houses at Çatalhöyük were built tightly packed together, without streets between them, and residents apparently moved across the settlement by walking along the rooftops, entering individual homes through openings in the ceiling. Burials were placed beneath the floors of houses, and walls were sometimes decorated with plaster reliefs and paintings depicting wild animals such as bulls and vultures, alongside cattle skulls mounted directly into the walls, suggesting that wild animals, hunting, and the surrounding untamed landscape retained real symbolic importance, even within a settlement that depended primarily on farming for its food. Pottery appeared as a widespread technology around this same general period in several regions, though not always alongside the very earliest farming, since some pottery traditions in East Asia actually predate confirmed agriculture in that region by several thousand years. Once established, pottery offered clear practical advantages for a settled, food-storing way of life, allowing grain and other food to be kept safe from pests and moisture over long periods, permitting new methods of cooking, such as slow simmering, that were difficult or impossible using only fire and simple containers made from wood, hide, or woven fiber. From its origins in the Fertile Crescent, farming spread outward into Europe over the following several thousand years, reaching Greece by around 8,500 years ago and, moving up the Danube River Valley, Central Europe by around 7,500 years ago. Genetic evidence from ancient skeletons recovered along this route indicates that farming spread into Europe markedly through the migration of actual farming populations, rather than purely as an idea adopted by existing local foragers. Since early European farmers show close genetic ties to Anatolian populations, distinct from the genetic profile of the Ice Age hunter-gatherer populations already living across Europe at the time. Over the following millennia, these two populations, incoming farmers and existing foragers, gradually mixed, along with a later, separate wave of migration from the steppes of Eastern Europe and Western Asia, producing the genetic ancestry pattern found across most of Europe today. A layered blend of three broad ancestral populations, rather than a single, unbroken lineage stretching back to the continent's original Ice Age inhabitants. By around 6,000 years ago, farming villages across the Fertile Crescent, the Nile Valley, and parts of Asia had grown into larger, more complex settlements, some approaching the scale of true cities, supported by increasingly sophisticated irrigation systems, organized trade networks, and early forms of centralized administration. Writing itself would not appear for another several hundred years, first developing in Mesopotamia as a practical tool for tracking agricultural surplus, trade transactions, and administrative records, long before it became a medium for literature or extended narrative. The city of Uruk, in what is now southern Iraq, stands as one of the clearest examples of this transformation. Growing by around 5,000 years ago into an urban settlement with a population likely numbering in the tens of thousands. Organized around monumental temple complexes, planned residential districts, and an economy dependent on irrigated agriculture, drawing water from the nearby Euphrates River. Managing a settlement of this scale required systems of record-keeping, resource allocation, and coordinated labor far beyond what any earlier human settlement had needed. The clay tablets recovered from Uruk and nearby sites, marked with an early form of writing called cuneiform, preserve some of the very first written records in human history, concerned overwhelmingly with practical matters such as grain quantities, labor assignments, and temple accounts. The mundane administrative bedrock upon which this new, larger scale of human organization was built. This point marks a natural place to bring this long story to its close, not because human history stopped here, but because the shift into settled agricultural life and the earliest cities marks a genuine turning point, the beginning of a different kind of human story, one increasingly shaped by written record, organized states. Rapid technological change, rather than the deep, slow patterns of biological and cultural evolution that had shaped every earlier stage of this long journey. Looking back across the full span of this history, a few threads stand out clearly. The shift to upright walking, tested gradually across millions of years by small, forest-dwelling hominins, eventually freed the body in ways that supported tool use, long-distance travel, and, indirectly, the growth of an unusually large and costly brain. That brain, fueled in part by an improving diet and eventually by the advantages of cooked food, supported increasingly complex behavior across a series of related but distinct human species, several of which coexisted for long stretches of time, sharing landscapes, exchanging genes, and occasionally exchanging ideas and technology as well. For most of this history, more than one type of human walked the earth at once. Homo erectus persisted in Asia, while Homo heidelbergensis emerged in Africa and Europe. Neanderthals and Denisovans developed in parallel across Europe and Asia, while Homo sapiens was still taking shape in Africa. Only in the final tens of thousands of years of this 7 million year story did a single human species gradually come to stand alone, without others to share the landscape, trade genes, or compete for the same resources. This long habit of coexistence, several human species sharing a planet, sometimes even sharing a single valley or a single coastline, leaves a strange and easily overlooked impression once it disappears. For millions of years, encountering another kind of human, related but distinct, would not have seemed unusual at all. It would simply have been part of the ordinary texture of the world, in the same way that encountering a different species of monkey or a different species of antelope might be unremarkable today. That texture is now gone, and has been gone for tens of thousands of years, long enough that most people alive today would never think to imagine the world any other way. Yet the genetic evidence recovered from Neanderthal and Denisovan bones makes clear that this more crowded, more varied human world persisted for the overwhelming majority of this history, and that its disappearance, however distant it now feels, is a comparatively recent development rather than some permanent, unchanging feature of what it has always meant to be human. The people who painted the walls of Chauvet and Lascaux, who crossed open ocean to reach Australia, who first gathered wild grain in the hills above the Fertile Crescent, were not fundamentally different from people alive today. Their brains were the same size, built to the same basic plan, capable of the same range of thought, emotion, and creativity. What separates their world from ours is not biology, but accumulated knowledge, passed down, refined, and expanded across several hundred generations, building slowly on itself in a way no single lifetime could achieve alone. Every technology explored across this history, upright walking, stone tools, fire, clothing, art, agriculture, arrived through the same basic pattern. Small, incremental changes tested against the demands of survival, occasionally preserved and built upon by the next generation, occasionally lost and rediscovered later by entirely different populations working independently toward a similar solution. No single invention explains the human story on its own. It is the accumulation, the slow compounding habit of building on what came before, that eventually produced a species capable of painting animals on a cave wall by lamplight, crossing open ocean without sight of land, and coaxing a wild grass into a reliable, storable source of food. That process of accumulation, of one generation learning from the last and passing something more forward to the next, began quietly, long before writing, long before agriculture, long before even the simplest stone tool. It began with the first hominin who stood upright on the African plains, looked out across an unfamiliar landscape, and took a first tentative step forward on two legs into a future no single individual could have imagined, but one. This entire species has been walking toward, one generation at a time, ever since.